Bom dia, pessoal. Hoje a gente vai começar a gente agora vai começar a palestra da professora Ana Quies Santos, da Universidade Federal do Rio Grande do Sul. É uma palestra sobre, eu acho que a gente chamaria de astronomia ou de astrofísica, no teu caso?
Astrofísica.
Astrofísica mesmo, né? Bom, então então é uma honra ter a professora Ana Quies aqui com a gente. A gente eu já tinha convidado ela para a série de seminários do semestre passado, mas acabou dando alguns problemas. Ela estava numa visita na China também, né? E aí os horários estavam um pouco complicados também, né? E aí agora acabou finalmente dando certo. Então já vou começar agradecendo pela paciência e pela oportunidade de dar o seminário aqui, viu? Então aqui um pouco sobre a biografia da professora Ana. Ela é uma astrofísica observacional. Ela fez o bacharelado e o mestrado em física na Federal do Rio Grande do Sul. Em 2007 foi para a Holanda, onde fez um doutorado na Universidade de Utrecht. Né? Passou 3 anos no Reino Unido como pós-doc na Universidade de Nottingham. Voltou para o Brasil, né? E foi para pelo que eu entendi, você pegou uma bolsa do Ciências Sem Fronteiras também como pós-doc na USP, é isso?
Uhum.
Pronto, e aí desde 2015 está no departamento de astronomia, no departamento de astronomia do Instituto de Física da Universidade Federal do Rio Grande do Sul. E ela recebeu alguns prêmios, recebeu esse prêmio da L'Oréal Unesco para mulheres na ciência, né? Hoje pesquisadora 2 do CNPq e membro afiliada da Academia Brasileira de Ciências, que foi inclusive como eu conheci a professora Ana. Eu encontrei, não sei se ela lembra, mas a gente se encontrou já em 1 ou 2 eventos dos membros afiliados da Academia Brasileira de Ciências. Né? Então, novamente, obrigado aí por dar o seminário. Você pode começar a partir de agora já.
Obrigada, Andrei, pela apresentação e pelo convite. Bom dia a todas e todos. Eu vou apresentar o seminário em inglês, mas a parte das perguntas, claro, pode ser em português. So this is the title of my talk, Globular Cluster Systems as Probes of the Buildup of Galaxies and Their Environments. And this is my research group at the Physics Institute of URGS, named Extragalactic Archaeology and Transformation of Galaxies, or EAT for short. Here are some of the faces in the research group. Part of the group focuses on understanding the transformation of galaxies, especially finding and characterizing jellyfish galaxies. But this can be a subject of a future seminar. One of our lines of research focuses on using globular clusters to understand galaxy formation and evolution from the Milky Way to galaxies at around comma distances. And here are the grad students that work on this topic. And here are the hardworking undergrads. And I highlight that for this line of research, we work with co-supervision with my colleagues Charles Bonato and Cristina Furlanito. For this talk, I'll give a long introduction to the field of globular clusters, starting from the Milky Way and local group galaxies. Then I'll review the main properties of globular cluster systems across a range of masses and environments, and in some of our own past work. I'll move on to present recent works from our group on the topic of GCs, especially on the nearby triplet of spiral galaxies MED1 and on low surface brightness galaxies we discovered recently. I will finish by showing prospects for the field in the coming years with the new generation of ground-based surveys and space facilities. So starting with galaxies. Today we have a pretty good idea of how galaxies are formed. We know that galaxies are formed hierarchically. We start from the cosmic web of rotating dark matter halos. And from this cosmic web of rotating dark matter halos, we have disks forming in dark matter halos from cooling gas. And if mergers between disk galaxies happen, we might create spheroids. And if more mergers occur, we have new disks that can grow around the spheroid if further gas cools. And here there's a simulation of the formation of a single massive galaxy through time from the TNG 50 simulation, a very famous recent cosmological simulation, where we see the hierarchical merging happening. So at the core of this hierarchical growth paradigm is the agglomeration of mass in galaxies by mergers and accretion. And how can we reconstruct the assembly histories in the outskirts of galaxies as assembly histories that bring up structures such as this one seen here in a galaxy in the local universe? How can we determine the fate of a galaxy? As stars, dark matter, and gas, they all seem to scramble up and erase the traces of the progenitors and of the processes that occurred prior to or during the merger event. And objects caught in the act of merging and just after a burst of star formation are quite rare in the local universe, and we have to often be guided by simulations. So we need to go out there and look for a population of objects within galaxies and their environments that can help testify to the combination of different progenitors and to any new star formation that occurs as part of this growth process. And this population are the globular clusters that are present in most galaxies. GCs are old stellar populations with ages reaching the age of the universe that are held together by gravity. Here is one such object from our Milky Way named M15. GCs are very bright. They contain around 10 to the 5 stars. They are ubiquitous in most galaxies, and their formation accompanies major star formation episodes in their host galaxies. GCs, when seen at distant galaxies, like this highlighted in the halo of one elliptical galaxy to the right, are like lighthouses that allow us to study the outskirts of galaxies at great distances. As mentioned before, globular clusters are present in most galaxies. Dwarf galaxies present from 0 to 10 globulars, ellipticals from hundreds to thousands, and spirals like our Milky Way from tens to several hundreds. Just a second, I'll get some water because my voice is not holding. So we could perhaps say that the field of globular clusters can be divided into two: the field of resolved globular clusters and the field of unresolved GCs. For resolved GCs, we can resolve and study individual cluster stars and measure their properties either through photometry or spectroscopy. And for unresolved GCs, we study the integrated light of the cluster as a sum of all the stars in the cluster. And we try to derive integrated colors, integrated spectra, and make use of a lot of stellar population models. The first obvious system to look for globular clusters is our own Milky Way. Our galaxy is composed of a bulge, a halo, and a disk, like in this cartoon scheme here on the top of the slide. And globular clusters are typically found in the spheroidal components of our galaxy, the halo, and the bulge. And here in the top panel, in blue, we have the distribution on the sky of the GCs, and in red of the dwarf galaxies as viewed by the very famous Gaia satellite. In the bottom panel, we have these same satellites and the predicted pathways from Gaia's proper motion. Measurements of GCs over the next 100 million years for dwarf galaxies, and the pathway of GCs over the next 10 million years. And over here I highlight the location of two globular clusters, one that is metal-rich, NGC 6528, and the other that is metal-poor, M15, that I showed before. So in astronomy, we refer to everything other than hydrogen and helium as being metals. So more metal-rich means that a given object has a higher amount of elements other than hydrogen and helium, if compared to a metal-poor one. In the Milky Way, the metallistic distribution of GCs looks more or less like this, a bimodal distribution with a peak of metal-poor objects and a peak of metal-rich globulars, and a few of intermediate metallicity. What about their ages? They are older than 10 billion years, but sometimes we cannot say with the current technology to place constraints from a 10 billion years old one or a 13 billion years old one. So we have still to improve the methods to determine ages. And how do we measure their ages and metallistic content so far? We take spectra and different images of different colors. For instance, here we have three objects that have a different metallistic content. One is a metal-poor one. Another is of intermediate age and metallicity, and the other is metal-rich. So these two are old. And there is somewhat a difference in their absorption lines. And over here, I highlight the location of the large and the small Magellanic Clouds, our neighbors. And here, I zoom in the SMC and LMC. They have a few old clusters, some of intermediate age, and some that are just a few million years old. So let's check it out. Here we have a metal-poor and old GC in the larger galaxy, and intermediate age in the smaller galaxy. In the same field, there is also a very famous globular cluster from the Milky Way, this one over here, 47 Tuc, that is old and metal-rich. The clouds also host many star clusters, younger, such as the Taranta Nebula, and these other guys here. In other late-type galaxies, such as our spiral neighbor Andromeda, besides being found in the bulge and the halo, globular clusters are also found heavily associated to streams, these structures here. And in the most massive galaxies, such as these two at the center of the Hydra cluster, they have an estimated number of 15,000 clusters, like this little dot inside the white circle. GCs are not only found in the bodies of their host galaxies, but also free-floating in galaxy clusters, not necessarily bound to a host galaxy. So the Virgo, the Fornax, the Coma, and this Abell 1689 galaxy cluster all appear to have rich populations of intra-cluster globular clusters. This beautiful super deep HST imaging estimated over 200,000 globular clusters in this single HST field. Here, each of these are galaxies, and here is the distribution of GCs. So when the first image of the new James Webb Space Telescope was released, it was very impressive to see so many little sources in the center of the SMACS 273 cluster at redshift 0.4 that I did stop all the work I was doing that day. I did post it on Twitter, although I only had 4 likes. Later on, the first archive preprints came claiming the detection and first analysis of GCs in this image, although they are still under review. This image is a composite from 6 different images at different wavelengths, over here. And in total, there's 12.5 hours of integration time, and at achieves depths at infrared wavelengths way beyond what the Hubble Space Telescope was capable of doing in their deepest fields, which took weeks. And inside, in this side image, you can see the zoom in from the center of the galaxy cluster with the GC candidates highlighted in green. Now a bit of context on galaxies and their GCs. Let's have a look at simulations, observations, and some scaling relations. So cosmological simulations of galaxy formation appear to show a two-phase scenario with a rapid early phase at redshifts greater than 2, during which in situ stars are formed within a galaxy from infalling cold gas. There's a followed phase that is extended and happens since about redshifts of 3, during which ex situ stars primarily accreted. In this later phase, massive systems will grow considerably in mass and radius by accreting smaller satellites that are formed earlier, outside of the Virgo radius of the central forming galaxy. And one known result from galaxy evolution is that massive galaxies show a substantial size evolution since about redshifts of 3, as we can see in this figure. We have the size evolution of massive galaxies versus redshift, both for spirals and disk-like objects. And we see that they grow in size from the past to the present. Here's a cartoon picture for the formation of early type galaxies, the so-called two-phase formation, as I mentioned, where we have a red nugget phase that you're going to find in the literature, where we have this in situ phase, happens at high redshift, followed by mergers in the last 8 billion years. And if we let it coalesce, we will end up with some massive galaxies we see in the nearby universe. It is possible, however, to find galaxies in the local universe that have not gone through this second phase and are like time capsules of high redshift universe. And these objects are commonly found in the literature as relic galaxies. And our group has done some work on this front, both in simulations to find these galaxies and in observations to characterize the GC systems of these relic galaxies. And how do we add the globular clusters to this picture of galaxy formation? So in optical colors, we generally see a bimodal distribution like we see in our own Milky Way. And in this picture, the red metal-rich GCs would form in the in situ phase, whereas the second phase over here would bring in the blue metal-poor population of clusters through minor mergers. And if we look at the age metallicity relations for Milky Way globular clusters in this figure, we have that the metal-poor ones may have been accreted from neighboring dwarfs because they tend to follow the age metallicity relations from the SMC and LMC, for instance, over here. While the more metal-rich GCs over here, the bulge GCs in the green region have different relations. And cosmological simulations tell us that cluster formation happens in a turbulent environment at higher Z. And here I show just some citations of state-of-the-art simulations, such as eMosaics, that is paired with the Eagle cosmological simulation, the FIRE simulation, and other semi-analytical ones that are paired with the Illustries that I'll go into detail later. Here we have the video of one of the eMosaic simulations showing the formation of a Milky Way-like galaxy. The gray shading shows the gas that is fragmenting, forming stars falling onto the central galaxy. And we see newborn stars blowing bubbles into the gas, with their intense radiation and supernovae explosions. The GCs are indicated by colored dots, where the color indicates the chemical composition. The blue are the metal poor, and the red, the more metal rich. Over time, the merging of the central galaxy with smaller satellite galaxies will bring a large number of globular clusters to the central galaxy. The ages, the chemical composition, and the orbits of these clusters will reveal the mass of the progenitor galaxy that they originally formed in, as well as the time at which they merged with the central galaxy. And these simulations show that the cluster formation, the globular cluster formation, peaked at redshifts of 2, in a similar manner to the star formation histories of galaxies. And observationally, we see that the ages of clusters are mostly older than 10 billion years. And this has been determined through careful analysis of spectra and images of different colors. And you might be wondering how images of different colors and spectroscopy work to measure ages and metallicities. So ideally, we would like to have spectra for each object we study. With spectra, we can measure the strengths of the different lines and compare to stellar population models. But spectroscopy is observationally very expensive, and imaging costs much less. And with less observational time invested, we can get colors of several objects in one go. And here I show the spectra in the left for one extragalactic GC from a recent paper. And all these colors represent images of different filters from one given survey. And by having images in several different bands, we can build what we call the SED, the spectral energy distribution. And by fitting a SED, we can then infer the properties of the objects by comparing to stellar population models. If we have less bands, less images, we can still use color diagrams, such as this one in the right, and still have some constraints on the ages and metallicities of the studied objects. And these models for GC formation predict that spiral galaxies, where GCs are less studied, should have a broad range in GC ages, and can be seen in these age metallicity relations shown for redshift 0. We can see a wide variety of age metallicity distributions, which arise to differences in their formation and assembly histories. And this is yet to be confirmed observationally. If we look at the GC systems, color distributions for different luminosities, different host galaxy luminosities, we have that the lower luminosity galaxies, the ones shown in purple, have almost exclusively blue metal poor globular clusters. Whereas the color or metallicities of both red and blue GCs, the GC peaks, they correlate with host galaxy luminosity, and dwarf galaxies metal poor GCs seem to be more metal poor than the metal poor GCs of more massive galaxies. And some color relations have been reported to vary according to environment. And here I show an example from the Virgo cluster. In the left panel, we have that from the center in red to the outskirts in blue-violet. These are several galaxies, M87, in the center of Virgo, and these other ones. And these color plots with, in black, stellar population models and Milky Way globular clusters. And we have that the Milky Way GCs, they seem to follow much more the relations for GCs in the outskirts of this image. Whereas in the center, they seem to be very far off. So there's some claims in the literature of environment effects going on here. And this was the subject of a PhD thesis of the group that we hope to publish at some point. Another interesting scaling relation is the number of globular clusters normalized per host galaxy luminosity, MV of -15. The specific frequency, or SN, seems to be high in both giant galaxies and dwarf galaxies, but universally low at intermediate luminosity galaxies. So coming back to Rayleigh galaxies, which are massive, compact, red galaxies and display old stellar populations. Here are 3 Rayleigh galaxies that fall well below the mass-size relation for local galaxies, this one in blue. And there are some results that show that in contrast to the Virgo GC systems of host galaxies of similar mass to the prototype Rayleigh galaxy, this one NGC 1277, NGC 1277 seems to contain almost exclusively red GCs, whereas the green ones here have the 2 populations, the blue and the red. And together with Carla Lamo Martinez, a former postdoc here in Porto Alegre, we analyzed the GC systems of 14 Rayleigh galaxy candidates with archival Hubble Space Telescope imaging. And these galaxies are all found to be outliers in this relation of the mass-size relation. And in fact, most of them will fit much better with higher redshift mass-size relations. And in this work, we try to quantify the richness of these GC populations through the specific frequency parameter, Sn. And we find that they are on where they should be as expected for Rayleigh galaxies. We can also compare the total mass of globular cluster systems to the parent galaxy mass. And here we have that the GC systems are connected to the properties of their host galaxies and show a direct relation to the dark matter halo of their parent galaxy. And this is still to be verified for lower mass halos, though. Also, there's an empirical relation that is more and more appearing in the literature regarding the number of globular clusters and the total mass of the host galaxy. By total mass, I mean the baryonic and dark matter masses together. Thus, by counting GCs, we can determine a lower limit to the total mass of a galaxy. And if we have other ways to measure the stellar mass, for instance, we may well determine a lower limit to the dark matter fraction. And to calculate the number of globular clusters, we use the globular cluster luminosity function, the GCLF, which is defined as the relative number of GCs per magnitude, and we can use it to also determine distances. The GCLF from the Milky Way has a turnover close to the V-band magnitude of -7.4, the absolute magnitude, not the apparent one. And the shape of the GCLF is very close to a classical Gaussian. So to estimate the number of GCs from a galaxy, we just fit the GCLF to the magnitude distribution of the clusters. And here are examples of GCLFs in the local group, the Fornax and the Hydra cluster. So as we increase the distance, we sample less and less the faint end of the GCLF. And now I'll show some recent and ongoing works, one on a nearby triplet of spiral galaxies and another on a sample of low surface brightness dwarf galaxies. Andrei, tá tudo certo?
Tá tudo ok, viu?
Tá tudo ok, só que a gente fica falando sozinho.
Pois é. É nesse sistema que a gente está usando, que tipo, os alunos não podem interromper, porque eles estão, tipo, os alunos estão vendo online pelo YouTube, né? E aí, tipo, o máximo que eles podem fazer é escrever perguntas, que aí, inclusive, vai ter uma sessão de perguntas no final, mas são perguntas escritas no chat, e aí a gente coloca na tela aí para você ver, sabe? Mas a gente até estava planejando em talvez comprar a licença do Zoom para que pelo menos alguns alunos possam estar online, ao vivo, e fazendo perguntas para ti, né? Para não parecer que você está falando sozinho. Mas não, você não está falando sozinho. A gente está mesmo assim. Pode continuar.
So I'll start with this work that is now published within the J+ collaboration, the largest compilation of GCs in the M81 group of galaxies. In this project, we studied the M81 group at 3.6 megaparsecs, where we have these three galaxies. And here is a composite image of three J+ bands and gas H1 maps. So we see that this system is a beautiful mess of interactions in the gas. And we wanted to look if we find traces of past interactions in the GC system. A bit more on the survey. So J+ is a survey precursor of JPAS in the Havalandre mountain in the north of Spain that is undertaking data from the northern sky in 12 bands. These shown on the bottom left, on the bottom right panel. The filters have been chosen to probe key spectral features, so they can be used for stellar population studies. This recent work, we report a list of GC candidates. We perform photometry ourselves and also make use of Gaia proper motions. And we start from a literature sample of 105 spectroscopically confirmed clusters, developed a customized statistical model to search for GC candidates that will account for data that's missing and errors. And we search for GC objects that look like GCs on the spectral energy distribution space. And we use PCA. And a search in a region of 3.5 square degrees will expand the current list of known clusters by quite a bit. We started with 7.2 thousand point-like sources that had photometry in at least 11 of the filters and about 100 spectroscopically confirmed clusters in the left panel. And we arrive at 640 GC candidates that are new, shown in the middle panel. In the right panel, we have the galactocentric distance versus the G-I color for the literature-confirmed GCs, and the GC candidates separated by their proper motion values. And the takeaway message from this analysis is that the confirmed GCs from the literature are in the range of intermediate to blue, and that the candidates with the lower proper motion, the orange markers, follow the same trend. And this is compatible with being halo and intra-cluster globular clusters. And we also seem to see tantalizing evidence for an overdensity of GCs connecting M81 and M82. And we seem to find no GCs very close to NGC 3077. We also look at a few examples of color diagrams and color distributions, which we will study in more detail in a future paper. But things seem to be making sense. And we map the Metalistic distribution function of the known spectroscopically confirmed GCs to the GC candidate ones and study their sets, and they seem to be compatible with that of globular clusters. And there's work in progress. We have gotten about 60 hours of Gemini 8-meter telescope in Hawaii to follow up the candidates. And we have more proposals under review where we're trying to figure out if these are real GCs or they're stars or other contaminants. And our goal is to do dynamical modeling of the system with the radio velocities. And now this last work that I want to show on the GC population and upper mass limits for low surface brightness satellites around our closest S0. Which I believe my colleague Cristina Furlaneto presented at the end of last year here at UFC. And the globular cluster part, we had quite some progress that we're currently finishing this, and it's led by Marco Canossa, an ICE student. So looking to study these low surface brightness galaxies in low density environments, our group obtained deep imaging from Blanco DCAM back in 2017. And this region around NGC 3115 is a low density environment, which does not have many massive neighbors around. So our first step was to visually inspect the area and search for low surface brightness candidates. So we found around 40 low surface brightness candidates in 2 dark energy camera fields of the Blanco telescope. And after the photometry, we obtained the structural parameters for these galaxies and found that 24 were consistent with being LSB dwarfs around NGC 3115. In this left panel, you can see the distribution on the sky of our candidate low surface brightness galaxies. And while inspecting the residual images of these candidates, we noted that several of them present point sources that could be globular cluster candidates. And here are the Blanco images. And then we follow them up with 6 GMOS pointings in the Gemini 8-meter telescope, shown as magenta squares in the left. And on the right panel, we have these 9 LSBDs for which we obtain GMOS imaging for. And after selection of GC candidates, we fit the GCLF, the globular cluster luminosity function, which I defined in the introduction part of the talk. The shape of the GCLF is very close to a classical Gaussian. So to estimate the number of GCs from a given LSPD, we use MCMC and obtain mean value sigma and other properties from the distribution of the number of GCs as a function of magnitude. Now that we have the GCLF from each low surface brightness dwarf, we can recover the number of GCs from each galaxy. We considered, based in other works from the literature, that these low surface brightness dwarfs with the less number of clusters are consistent with not having GCs. In the first plot, I showed the number of GCs versus their magnitude in the V-band compared with other works. And there's also a green point from one of the more massive ones that was previously studied with the Hubble Space Telescope. And here we can see that the GC system of this outlier here, what we call LSBD 22, is very contaminated, so we don't trust this data point, as this galaxy in particular is close to a very massive elliptical galaxy much further away. So we end up getting their GCs, the GC system of this other galaxy contaminating our object. And in this other plot to the right, I showed the specific frequency versus the magnitude in the V-band. And these 2 points here, one is an LSBD, the LSBD 22, that has a lot of contamination. And the other one, the model didn't fit very well. So arriving to the end of this part, the take-home point is that by using the number of GCs, we may well also recover the upper mass limit to these low surface brightness dwarfs. And the results achieved here seem to make sense comparing with other similar systems. Now, approaching the end of the talk, let me quickly mention the prospects with the upcoming facilities, both from space and from the ground. These are facilities to keep an eye on for this kind of work. Of course, I'm biased, as these first two from the ground I'm part of. So let's have a look a bit about a bit more in details on Rubin, LSST, and JPAS. So the Rubin Observatory consists of an integrated system that combines a 8.4 meter primary mirror and the world's largest digital camera. In fact, this week I was in the Brazilian news. The 10-year Rubin Observatory Legacy Survey of Space and Time, LSST, will image billions of objects in these 6 optical colors shown here. The survey, which will cover over half the sky from Chile, also will record the time evolution of these sources, and it will be the first motion picture of our universe. JPAS, the Havalambre Physics of the Accelerating Universe, is a more modest project between Spain and Brazil and consists of a 2.5 meter telescope, but it has 59 filters. It will not go as deep as LSST, of course, but will provide a poor man's spectra for many sources. And this will be wonderful for the study of stellar populations of galaxies and their globular clusters. And the space facilities, I highlight Euclid, CSST, and Roman. Euclid is from ESA, and Roman W1 from NASA. CSST is the Chinese Space Station Telescope, while Euclid and Roman are in the near-infrared, the CSST in the optical and ultraviolet. So talking humanity-wise, the Chinese Space Station Telescope will be kind of a substitute for the HST that has been working for quite many years, and it won't last forever. While Euclid and CSST are expected to be launched in the next couple of years, Euclid was severely affected by the Russian-Ukraine war, as it was going to be launched with a rocket from Russia. But yesterday, according to ESA's Twitter, they have set an agreement with Elon Musk's SpaceX to launch Euclid. And this is quite interesting, but scary partnership in some sense. So to have an idea, here is the field of view of CSST. Euclid and Roman W1 compared to HST in orange and yellow. So it will be a huge step in maximizing the efficiency of the observations. And last but not least, here are the limiting magnitudes these surveys will achieve, with LSST going very deep, the deepest of all, over here. And with the Chinese Space Station Telescope being slightly shallower, but in the same filters as LSST, but from space with better spatial resolution. Thus, we will be able to probe the near-complete GC systems of galaxies out to about 200 megaparsecs, 0.05 in redshift, from all morphologies and environments. So I hope I have convinced you that GCs are powerful probes to understand the evolution of galaxies, including dark matter in galaxies. And here I presented some of our group's work on GCs in relic galaxies, the M81 triplet, and in low surface brightness dwarfs, and showed that the present and near future are photometric surveys that will give us a near complete picture of GCs out to 0.05 in redshift for different galaxies, morphologies, and environments. Obrigada.
Bom, muito obrigado pela palestra. Viu? Agora a sessão está aberta aqui para perguntas, então os alunos que tiverem dúvidas aí podem mandar mensagem pelo YouTube, vou escrever aí já eu coloco, quando aparecer alguma mensagem, eu coloco aqui na tela para você ver também a pergunta, certo?
Vou parar de compartilhar a tela.
Enquanto os alunos anotam aí alguma pergunta, eu já tenho algumas perguntas para fazer também. Apesar de eu não ser bem da área, então as perguntas vão ser um pouco ingênuas, talvez, né? Mas com relação às simulações que você tinha mostrado aí, você mostrou alguns vídeos com simulações, né? Aí essas são simulações feitas por, tipo, tem alguns grupos que, todo grupo faz simulação desse tipo, ou tipo, essa é uma simulação já de... Porque eu imagino que a acurácia desse tipo de simulação deve ser bem pesada, né? Porque é uma simulação com vários pontos, né? Então, assim, você pode falar alguma coisa sobre essa questão de como simular aquele tipo de vídeo que você coloca de formação de galáxias, o que é colocado naquele tipo de simulação?
Certo, então, essas simulações, eu lembro quando eu era aluna de mestrado, saíram as primeiras que eram só com matéria escura. E agora, a gente tem, já fazem alguns anos, com gás também. Então, as com gás estão bem mais realistas. Mas também tem alguns problemas nessas com gás. Então, eu posso falar de duas. Eu não trabalho exatamente fazendo as simulações, não é a minha área, mas a gente usa bastante as simulações para comparar com as observações. Porque como... bom, vamos falar assim, tem duas principais agora, a Eagle e a Illustris. Elas são meio competidoras, apesar que a pessoa que fez os dois códigos é a mesma, dos dois. Vai matéria escura, gás, estrelas, mas é uma simulação cosmológica, então começa dos primórdios e vai evoluindo num cubo. E eles estão disponibilizando os dados para qualquer um baixar e trabalhar com eles como se fossem observações. Então, é muito legal, porque toda a comunidade tem acesso. Então, é isso que a gente faz, a gente usa como se fossem observações de um banco de dados. Mas para saber mais...
um custo computacional alto ou alguma coisa assim?
Muito alto, muito alto. A gente aqui no Brasil não teria condições de realizá-las.
Mas aí eu vi que nas perspectivas de trabalhos novos que você tinha colocado tipo uma modelagem dinâmica. Aí essa modelagem dinâmica não é exatamente esse tipo de simulação, não, então, né?
Não. Daí a gente quer usar... a gente quer usar as velocidades radiais, que daí a gente pode ajustar alguns modelos para tentar ver a quantidade de massa que está encapsulada pelas velocidades que a gente consegue determinar. Então, isso que
mas é uma coisa
fui
mais
aprendendo.
Não tem uma simulação de tudo, não, né?
Não, essas são bem mais não pesadas, não tão pesadas computacionalmente quanto essas cosmológicas.
Ok. Aí, uma outra pergunta sobre os trabalhos que você tinha colocado como os ongoing projects, né? Eu vi que no primeiro que você colocou lá, desses ongoing projects, você tinha os dados, e aí nesses dados você estava analisando os dados e definindo o que é que são candidatos a esses Globular Clusters, e aí então, o que é que define exatamente se ele é um bom candidato ou não, e tipo, você está buscando só os que são novos, ou como é que é, o que é exatamente que tem nesse novo projeto? A ideia é procurar novos Globular Clusters ou identificar qualquer um que já esteja lá naqueles dados? E de onde vem os dados também? Essas são as duas perguntas.
Certo. Então, esse que a gente está tentando finalizar esse artigo, os dados primeiro vieram do Blanco, do Dark Energy Camera, que é o mesmo que fez a mesma tipo de observações do DES, do Dark Energy Survey, que vem do telescópio Blanco no Chile. É um telescópio de 4 metros. Esses eu observei eu mesma, eu consegui os dados, escrevi o proposal e fui lá observar. Daí, a gente está tentando... A gente primeiro estava em busca das galaxinhas anãs, em volta ali da NGC 3115. Daí a gente, trabalhando com elas, viu que algumas delas têm uma sobredensidade de fontes pontuais que pareciam Globular Clusters. Então a gente aplicou para o Gemini, que é um telescópio de 8 metros, que o Brasil faz parte do consórcio, que tem um telescópio no Chile e outro no Havaí, em Mauna Kea. Então, a gente conseguiu os dados e daí, como é um telescópio de 8 metros, a gente consegue... é melhor, então, para a qualidade dos dados para identificar os GCs. Mas como é que a gente identifica? A gente usa... a gente faz a fotometria, então, determina a magnitude, vê as cores, se são compatíveis, a forma do objeto, se ele está mais compatível com galáxia de fundo, com estrela, mas daí, para determinar se é mesmo um globular, a gente precisa de um espectro. E para obter espectro, não nos dão tempo bem tão facilmente, é muito caro observacionalmente, então...
É uma série de medidas que você teria que todas elas, se tem aquilo e aquilo, você vai ticando as caixinhas para ver se aquilo cabe ou não no Globular Cluster, né?
Isso.
Então, tá ok. E uma outra pergunta mais técnica, mais prática aqui também. Eu vi que você mostrou nessa figura do Rubbing LSST. Na figura lá tem o telescópio, e tem as pessoas vestidas como se elas estivessem numa sala, tipo uma clean room. Assim, pelo menos na área de sólidos, seria tipo o que você faria se você estivesse trabalhando com coisas muito pequenas e tal, que não podem ter sujeira, coisa desse tipo, né? Por que é necessário por que é necessário eles estarem vestidos daquele jeito para trabalhar no telescópio? Eu não sei se puder colocar
aqui...
assim, porque não está compartilhada a tela, né? Então, se o secretário puder colocar a tela aí.
Aqui, essa aqui?
Isso aí, tipo, geralmente esse é o tipo de coisa é o tipo de vestimenta que a gente usa em sala limpa para fazer dispositivos eletrônicos, né? Que aí você não pode ter nenhuma poeirinha nem nada, né?
Mas é isso. É isso mesmo.
É para isso também, né?
Também estão parecendo o pessoal contra o Covid da China também. Não, eu coloquei essa imagem... Ainda está assim
até esse ano, tá?
Sim, tá, o Covid 0. Eu fiquei 2 meses presa. Essa imagem saiu essa semana. Que saiu até no G1, tem uma reportagem da maior câmera do mundo.
Mas é também então relacionado ao fato de você não poder ter sujeiras nas lentes ou coisas desse tipo, né? Dos detectores,
sim.
né? Ok. Deixa eu ver aqui, os alunos ainda não colocaram nenhuma questão.
Se quiserem me escrever depois, tudo
bem. Pois qualquer coisa pode mandar e-mails para ti, né? Eu tenho mais uma pergunta técnica aí, agora com relação aos dados que você tinha colocado de número de GCs, desses NGCs como função do N, e aí tem os dados desse artigo do Lin et al. Em 2018. Então, se puder colocar a tela novamente aí, o secretário. Pronto. Acabou de aparecer a tela, mas sumiu de novo aqui. Pronto, está voltando agora. Pronto, na verdade, eu acho que são os slides... faz parte desse mesmo grupo mas os slides anteriores. Que a minha dúvida...
Esses são dados observacionais. É uma relação empírica. Essa aqui.
Pronto, esse, por exemplo. Nesses aí, esses dados roxos, eles estão tão espalhados, aí eu não entendi muito bem porque ele está meio fora do que parece, por exemplo, dos outros 2 artigos, do teu e do...
Bem lembrado. Então, assim, essas galáxias aqui, elas são bem mais massivas. E essas galáxias, tem bastante estudo sobre elas, as UDGs, Ultra Diffuse Galaxies, que tem umas que tem muita matéria escura e outras tem pouca. Então, não se sabe exatamente as razões, mas parecem ser 2 tipos de galáxias, né, nessa região aqui, e esse é no aglomerado de Coma. E no aglomerado de Coma ele é bem mais massivo que o ambiente de Fornax e o nosso trabalho. Então, é uma questão também de ambiente.
É de onde eles estão olhando, por isso que fica tão separado, né?
Isso.
Okay. Não, tá bom. E uma última pergunta aqui, que é talvez assim, não sei se é necessário ou não comentar, mas que você tinha dito que a colaboração do International Space Station com a SpaceX, por exemplo, é uma coisa que pode ser um pouco controversa. E aí, nesse caso, qual seria a controvérsia do seu ponto de vista com relação a isso?
Não, é que assim, não é a International, é a ESA. ESA. Então, que como tem a guerra acontecendo, a Rússia não está participando, pelo que eu entendo. E a controvérsia que eu coloquei é que a primeira vez assim que eu vejo que se vê o Elon Musk e a SpaceX tem muito receio dos astrônomos, porque eles colocam essas como é que é, as satellite constellations, e para o ground-based astronomy é muito ruim, porque estraga o céu, estraga as imagens. Então tem bastante briga assim no ground-based, mas para lançar um satélite, para lançar um telescópio, o Euclid, então o acordo foi feito. E eu achei interessante, saiu ontem isso, porque estava todo mundo assim, agora com a guerra, como é que o Euclid vai ser lançado? Esses projetos são de muitos anos. Então, o JWST mesmo demorou muito tempo, demais.
Eu imagino. São experimentos que assim, são planejados para uma década antes para poder começar a ser feitos, né?
E mais até.
Né? Então, tá ok. Bom, então, não apareceu nenhuma pergunta por aqui. Qualquer coisa que, se alguém tiver dúvidas, a gente podem mandar as perguntas para mim e eu passo para a professora Ana também. Então, novamente queria agradecer a palestra, viu? E tá aí de portas abertas também, se quiser colaborar com o grupo, talvez. Eu não sei se a gente já teve aqui uma palestra há 2 semestres que você tinha até mencionado também aqui, né? Que no final do ano passado.
A Cristina.
Era a Cristina, exatamente. Mas, assim, o grupo que tem aqui de astrofísica, eu não sei se é um tema que dá para colaborar também com vocês, mas qualquer coisa seria bom, talvez, conversar, né?
Estamos sempre abertos.
Tá bom, viu? Mas agradeço mais uma vez a palestra e um bom dia aí para vocês, para todo mundo aí da audiência também, viu?
Bom dia. Tchau,
Bom dia.
tchau, gente.
Tchau.